Hello, everyone. Welcome to this meeting in our CS Colloquium series. We're extremely excited to have Leo Joskowicz speaking today. Leo is a professor here at the School of Computer Science at the Hebrew University. He is the founder and director of the Computer-Aided Surgery and Medical Image Processing Lab. He's a fellow of IEEE, ASME, and MICCAI. He's the president of MICCAI Society. He has won numerous awards, including the Emory Smoller Award in 2010 and the K Innovation Award in 2007. He has published hundreds of technical works, including in journal papers, book chapters, editorials, and patents. He's on the editorial board of 6 journals, and he's naturally an extremely busy person, so we're very happy to have him here with us, telling us about his recent works. So the stage is yours.
Thank you, Ilan. Thank you for the very kind introduction. Welcome, everybody. I encourage you to ask me questions, clarification questions, or more general questions. I will make pauses during the talk so you can ask questions, but feel free to write on the chat so Ilan can tell me, or just unmute yourself and ask me a question, okay? So the topic of today has to do with medical image analysis in radiology. I chose today to give more of an overview talk rather than a highly technical talk. There are technical aspects to it, but I'll just go over them so you get the general idea. This is a joint work with a variety of people, including the CASMIP lab students here at the Hebrew University, Professor Daphna Ben Bashat and Dr. Liat Ben Sira at the Tel Aviv Suraski Medical Center, Professor Jacob Sosna at the Hadassah Medical Center, and others that I will mention during the talk. So this is the topic of today. We're talking about radiology and medical images. What you see here is a CT image of the body. You see here on the right side the original axial slices, and what you see here on the left is 3D reconstruction, a visualization of the organs inside the body, and what you see here. This is a typical image. It's basically a sampling of the body with about 400 axial slices. Each slice is what you see here on the right, and the slices are 1 millimeter apart. And the idea is that people get CTs or MRIs to know what happens inside the body. And this is already very ubiquitous nowadays. There are everywhere, and there are about 250 million CT images and about 250 million MRI images and about 750 million CT images worldwide, and this is not counting X-ray, ultrasounds, and other modalities. In this talk, I'm going to focus mostly on volumetric images, which is CT and MRI. So what is computational radiology? The idea is basically to extract qualitative and quantitative information from these medical images for some clinical purpose, reporting and decision making. So for example, we see here the first image on the right, the detection of sacroiliitis. This is a degeneration of the sacroiliac joint, the pelvis. What you see here in red is the analysis of the joint region on those axial slices you saw before for diagnosis. Here in the middle, you see a 3D reconstruction of liver and the liver tumors. You see in red the blood vessels, in dark blue the liver contour, and in green the tumors themselves. And the purpose here is to understand where are the tumors with respect to the blood vessels and what kind of treatment can be taken. A third example would be surgery planning. This is an MRI image of a brain. This is the axial slides. What you see here in the middle in green is a delineation of the tumor that is going to be irradiated with radiosurgery, and the purpose of the planning here is to determine what is the contour of this tumor and what kind of dose and what direction should the dose be applied. So as you see, the medical images have a variety of uses throughout the clinical work cycle. And nowadays, in the last few years, there's been a lot of buzz in the combination of artificial intelligence and radiology. You see mostly publications from the radiology journals. The radiologists are the people the clinicians who are responsible for the medical images in the hospital. Here just a very scant sample of different examples. This is a mammography to detect tumors in breasts. Different companies using AI and deep learning, including several here in Israel. Here's an example of one. The Radiological Society of North America has even launched a journal for radiology and artificial intelligence. This was very recently, and a very recent conference this past month reached over 2,500 participants, just dedicated on the subject of medical image processing. So as you see, there's a lot of interest about this topic. And even some of the buzz goes to the extent of saying, is AI going to replace radiologists? Will it doom radiologists? Well, we've heard that before. And this is, of course, hype. Nowhere near as fully autonomous cars are going to replace drivers. However, the advances are interesting. So I don't think AI is going to replace radiologists anytime soon. But what will happen, and this is the subject of the talk, is that AI will replace radiologists that don't use AI. And we'll see why. Okay, so the call here is that all the buzz is about developing tools that are useful for radiologists and clinicians to do better their job. And I call this, so what are the current trends? I call this in general, instead of calling it AI radiology, I call it computational radiology, because this is really what this is about. And the goal here is to develop tools. Yes?
Somebody's asking, what is radiosurgery?
Radiosurgery is a surgery performed with radiation. It's a radiation therapy with a high intensity beam. Okay, there's going to be a number of medical terms that you might not understand, but it doesn't really matter because this is a talk that's tailored to computer scientists. The example was meant to illustrate a treatment. So I'm going to use a number of names that you might not understand, but only it doesn't really matter for the talk. Okay. Okay, so what are the reasons that there is such buzz and the trend is going on? First of all, obviously the patient volume increases, the quality of the images has increased, the number of patients increases faster than the number of radiologists and clinicians. So you see here a radiologist looking at a scan, the scan we saw. We said that each one of these volumetric scans consists of several hundred images, and they have to look at them one after the other to understand what's going on. So first of all, there is a clear shortage of manpower, and also the number of images that each radiologist has to look at is very diverse. It's very diverse, and there are many of those. The resolution increases, and therefore this causes the cost to raise as well, because you have to pay more radiologists to look at the scans. The scans take longer to look at, and the treatments become more and more complex. So the planning and the amount of time each radiologist has to spend on each of the scans also increases. And this has to do, of course, with the complexity and diversity of the treatments, which fortunately are developing and really increasing at a very fast pace. So all this is creating a tremendous pressure on the health system and on radiologists in particular to have them some help in interpreting the images that have been acquired. On the other side, if you will look at the technical factors, Nowadays, big data becomes ubiquitous. Large scans are not a problem anymore. Large amounts of data can be transferred through the internet without any problem. So there is no barrier anymore in terms of the size and the bandwidth that you need. Okay, and also, and this is also the focus of this talk, the new AI technologies have been an enabler to this kind of to meet this kind of challenges. So, from a clinician's point of view, this is really all about automation, but not only automation, about the optimization of the workflow. So, to put it in the paradigm shift that we're looking for is not automation, full automation of radiology as the statement that radiologists are going to be replaced, but really we're looking at automation, optimization of the workflow. And let's just take two parameters. We said that one key parameter is the radiologist time, that you see here in the horizontal axis. And the other one would be the accuracy. Let's say you need to make a diagnostic or to measure something to a certain accuracy, okay? And of course, 100% accuracy is not always necessary, just like if you have speed trap cameras in the highway, the camera doesn't have to be accurate to 1/10 of a kilometer. It's enough that it gives you plus minus 5 kilometers an hour to know that if you get a ticket or not. So each clinical requirement has a different requirement in the terms of the accuracy that you need. Let's just take these two parameters. What you see mostly in current practice in many cases is that due to lack of time, this is performed fully manually. And due to lack of time, in many cases, the clinical requirement, the accuracy required for the clinical requirement is not met. What we're looking when we're thinking about computer support is basically moving the curve to the left. What this means is the following. We don't want something fully automatic, but we want a new practice in which the accuracy is above the clinical requirement, and we want to quantify what this clinical requirement is. And we want, of course, less time and more accurate. That's already a big gain. But in addition, we want to talk about the observer variability. You have certainly experienced the case in which you go and ask one doctor one thing and then to go to the next doctor and he tells you or she tells you something different. And this might be perfectly legitimate simply because there's uncertainty in what different causes. So it is well known in radiology that something called observer variability, which means what are the different types of diagnosis or segmentations that can be derived from different expert radiologists. And this, think of this as a certain variability or certain uncertainty band, okay? And what you see nowadays is that in current practice, this band can be quite wide, okay? Not only in terms of the classification of the disease, but also in terms of the actual measurement. And what we're looking for is to reduce this, first of all, to quantify what this observer variability is, and of course, to reduce it so that it is above the clinical requirement. So this is a little bit abstract, but sets up what is the goal, the practical goal of computational radiology. So the third aim is to lower this variability, okay? So in terms of clinical goals, if you manage to develop a tool that improves the accuracy, reduces the variability, and takes less time, this is going to yield a better treatment, okay? Any questions up to now? Okay, so to bridge the gap between the technical tasks that we have to do and the clinical tasks that we do, let's just take a simple example so you understand what is the transition between technical tasks and clinical tasks. For example, what you see down here is a CT and of the lung area. The black is the lung. You see here a tumor. This is a lung tumor. And remember, you have a set of slides because this is a 3D sampling of the body. Now, what are the technical tasks in terms of image processing? You can detect the area where the tumor is. You can identify it as a tumor and not, for example, as a cyst or as a bleeding. You can classify it, for example, if it's a malign tumor or a benign tumor. And you are interested also in the volume. For example, you want to know the segmentation to understand exactly where are the limits. And if, for example, you have a scan from last year, you want to know if there was some progression. Now, all these technical tasks eventually translate into a clinical task. For example, triage has to do with the detection of bleeding in an emergency room. For example, you want to raise a flag. It doesn't really matter what's the extent. You just want to call the attention of the attending physician. Hey, there is something going on here. Please take a look at this image. And this is called triage or ranking. Incidental finding means you take a scan for one reason and then suddenly you find a tumor. For example, in this case, it might be that there was a body CT acquired to examine the liver, and the radiologist notices that there is a tumor in the lungs, and this is called an incidental finding. You can have volumetry. For example, is it a small tumor or a large tumor, and what is the position? Or follow-up, as I mentioned, to compare it with what happened last year. So from a clinical point of view, what you're interested, for example, for the follow-up, is to know that there is a lung tumor here, that the volume is 22 cc, and this has been a progression as compared to what happened last year. Okay, so as you see, there is a correlation between the two sides, but of course, one has to bridge this gap. Okay, and I'm going to focus on this talk mostly on classification of voxels, which is basically the part of the segmentation. And this is certainly a fundamental task in many of the clinical challenges that there are, and this is a difficult task. Okay, so just to set up the context, let's talk about how do we go about classifying voxels. Well, we know how to do that. Basically, you have to create a model. You have a set of parameters and some relations between them. Okay, so that you can say all the black, all the red voxels. A voxel is a pixel, a unit of space instead of a unit of area. So to do this classification, you basically have three approaches nowadays. You do manual modeling, what we used to do a long time ago, which basically you manually set the features such as the intensity, texture, shape, and location of the tumor, and then manually construct the relationship between them, the boundaries, the differences, and so on. Machine learning allows you to still manually create the features. You can choose intensity, texture, shape, etc. You can choose more, about 10 to 50 of them, and then automatically you derive the relationships based on a number of methods such as regression, SVM, and other advanced tools. And recently, deep learning basically has the promise of automating everything, both finding the features and the relations between them. Okay, so I'm going to concentrate in this talk in deep learning. Deep learning has had great success in many areas, and I'd like to investigate what does it take to make deep learning work in radiology. Okay. I can already tell you that there's a very, very well-known axiom, which is called the no free lunch axiom, that tells you that things are not as easy as they look. Each one of these three approaches requires an effort and the data. The type of effort and the data is different. For example, in manual modeling, you only need a few examples. You need to interview the radiologist, understand what's going on, and then code that, okay? In the other extreme, for deep learning, you basically can tell the clinician, I don't really need to understand what you're doing, just send me the data, give me examples, and based on that, the network is going to learn by itself. So you can see that the nature and the type of effort is very different in each one of the sizes. And what I want to focus on is how does this differ in the case of radiology, okay? So some radiologists fear that this is going to be the future for them. Basically, they're going to become annotators. you and me cannot do the annotation because it requires quite a number of years of study to understand how to annotate and how to classify these things. And of course, the issues, the annotations are really the fuel for deep learning. And deep learning is a Ferrari, but it requires very expensive fuel and lots of it. And I want to see what does this mean in the context of radiology. So we're going to look at the annotator expertise, the time budget, the annotation quality, the cases distribution, because of course deep learning is based on having a sample of the space that you're learning, and of course also quantifying this observer variability. Are there any questions before I go on? Okay. Okay, so let's look at some of these cases. Some of these are well known, but let's say what does it mean for the medical images? First of all, the case distribution. We know very well this long dinosaur tall. It has to do with the frequency of the different cases. You're likely going to train your network with the common cases that have a high frequency. You get some of those examples, and for the vast majority of cases that come from here, you're going to get excellent performance. And this is what we've seen in other domains. However, what happens with the rare cases, we can see that they're quite far from these common cases. And it's very unlikely that you can gather these cases in your training set. However, this is the norm. You cannot just simply say, sorry, I have not seen this case. There's nothing I can do about it. So you have to incorporate in your scheme some method to bring in and identify these rare cases and do something about it. Not just saying, I have not seen this case is not acceptable. Let's talk about observer variability. Okay, what I'm showing you here is the same tumor, and this is looking at the slices, the axial slices on a CT. And this is the team of the radiology department headed by Professor Sosna at the Hadassah Ein-Kerem Hospital. And we ask these 10 people, both experienced and not experienced, to delineate the tumor. Tell us where is the boundary of the tumor. And this is the result. What you see here is one color per radiologist. Sorry. Okay. You see one color per radiologist. All of them are correct segmentations. So all the delineations are correct. What is the reason that you see variations? Well, obviously, there is variability. There are regions in which there's nice contrast up here, so there's little variability. But there are other areas where you see very high variability. Up here, simply you hardly see the boundary, and therefore it's bound to different interpretations. Note that all of them are legal, are correct segmentation. So in a study we did with them, or 4 different structures, we see that this variability can be between 5 and 57%, meaning the variability of the area or the volume that you can see. And this changes a lot by structure, case, and observer. And all of them are legitimate. So this is an intrinsic variability. It's not an error. In a different study, we show that this variability can be quantified and estimated. And this is a variability that can be quantified per scan and per patient. So I won't go into the details of how we do that, but basically it can be done, and it's important because it sets the baseline of what you want to do. So what are the bottlenecks? First of all, you need a large collection of representative data sets of scans, 1,000 to 5,000 for segmentation, and even more for classification. The manual expert annotation requires many radiologist hours for the initial deployment, and then some more for robustness and coverage to basically able to take into account all the missing cases. And also, if you think about it, each solution is going to be what's called narrow AI. Think of this as a radiology app, and you have hundreds of them because you have hundreds of organ structures, pathologies, and imaging protocols. So if you go about going this way, this is going to be a long-term endeavor, and it's a lengthy and costly development process that requires a lot of iterations, and of course requires a regulatory approval to be able to use that. So what is the problem with narrow AI? Basically, you have many specialties, you have many modalities, and each one of these boxes is one app, okay? And in fact, this is has more dimensions, because even if I just pick spine problems in CT, you're going to develop a very specific one. And this is going to be very, very not going to be cost effective for the vast majority of the common conditions. So the current paradigm also is not fit to do this, because you basically collect many scans, develop your program or deep network, deploy it, and then the evaluation requires fixing this, collecting more, and so on. So this is basically a sequential process. And what we're interested in, and this is the argument of this talk, and I'll show you how to do that, is that you need to involve the radiologist in all the stages. You collect a few scans, you develop a model, you deploy a working model that is not perfect, but allows the clinician to make the corrections, and basically moves on. Okay, and this, I'm going to show you, optimizes the radiologist time budget and the software development. So basically, think of the radiologist-validated annotations. What we want is to get the top of this pyramid, which is the high-quality annotations that are made by at least 2 experts. And here in the bottom, you see many that are done, for example, by a network. So in this pyramid, you have different qualities. You want very high-quality data sets, but this is going to have a very high cost. Okay, so you want to start with a low mixed quality with a network that was trained with a few examples. And basically, you want to optimize the radiologist's time and the correction in order to train a network and do better. So basically, the optimization function that you're looking for is to optimize the radiologist's time to do the correction. So what we do in the lab is that we have developed a methodology to deal with this problem, to be able to deploy quickly different applications for different pathologies and parts of the body. The first one is a fetal development in MRI, which I'll talk in detail. I use as a case study for doing that. But I just will mention quickly that we have other things such as tumors follow-up in the liver, lungs, and brain, and also in ophthalmology. So to be very concrete, let's take the first example and walk you through what would it take to build a tool for radiologists for doing fetal development in MRI. So the story is the following. In some cases of pregnancy, women undergo MRI because MRI shows much better the structures and the structures of the brain than ultrasound. So in about 1 to 2% of the cases of pregnancies, this is required. So this is what the fetal MRI looks like. You see here the fetus and the rest of the structures. And the goal is the following. You want to segment the body and the brain and the placenta. The placenta is a very important part for fetal development. And basically, based on these, you're going to do a number of measurements, morphometry, brain symmetry, sulcations, and you can also do a number of linear measurements. And based on this, you basically end up with a quantitative report. And this is what's missing nowadays in the clinic. You would like a comprehensive quantitative report. Based on this quantitative report, you can then compare for a specific fetus, what is, for example, the volume here, and then place it with respect to the fetal development curve from MRI, and then come to the conclusion whether there is a problem or not. In this case, it is in the lower 10 percentile, so there is a growth restriction to the fetus, and then a treatment can be applied. Okay, so the goal is to automatically generate this quantitative report, so that the evaluation can be done in a precise way. And the second goal is to develop these fetal development curves from MRI measurements, which are non-existing nowadays. So what are the challenges here? As I said, many slices. You have the three different structures. You don't know what the observer variability is, so you don't just want to give the volume, but also plus minus how much. The scan variability, there's a number of scanning protocols. Here are some of the names. The resolution and inhomogeneity in these scans is quite significant. In addition, for fetuses, there is a significant shape variability in the fetus and the brain, according to the gestation age. And you have anomalies because, of course, you're looking for pathology, okay? And many other problems that cause this. And of course, you have class imbalance because you're going to train a network, but you don't necessarily have the luxury of scanning many healthy fetuses, for example, or those with a certain pathology. So what I'm going to describe now is the overview of how do we go about building such a tool. So the first thing in the accelerated pipeline is the following. First of all, we do ask 5 to 10 manual segmentations for each one of these structures. Then we're going to train a deep network for each one of the structures. We're going to ask the radiologist to make corrections and train a network to learn how to make the corrections, okay? And this is going to give, this is going to produce about 50 high quality scans, annotations, with which we can now train the new network and now start scaling up the production of high quality segmentations. We're going to do a segmentation error estimation by uncertainty. We're going to do automatic segmentation error correction. And then of those that there is sufficiently high uncertainty, we're going to ask the radiologist to correct, but this time only to correct and only a few selected ones, okay? And based on that, we're going to achieve a high quality network. So this is the idea for the interactive correction. We start with a network trained with very few cases, in this case,
Leo?
age. Yes.
Leo?
Yeah.
Can you please repeat it one more time? It looks like the key point in the lecture. If you can repeat it, it would be great.
Okay, so what I'm going to describe now with an example is an accelerated pipeline. So this is, remember that the goal is to generate many high quality annotations that were validated by radiologists so that we have robustness and coverage, okay? And we're going to do this in two phases. Okay, instead of asking radiologists, please annotate 500 data sets for me, we're going to do this in an incremental fashion, and this is what I'm going to describe now.
I have a quick question. Yeah,
sure.
Why can't you use existing examples? Is it just matters of regulation?
No, there are many CTs and MRIs, but nobody has delineated. For a training network, you have to give examples to train. Okay, so basically you don't have the delineations.
Okay, so access to examples, it's not an issue, it's just about annotating
It
them.
is an issue, but it's not the
okay.
main issue. The main issue, of course it is an issue. There are some data sets, public data sets available, but very few of them, if any, have the annotations.
Mm-hmm.
Okay.
But this is a one-time process that you need to do forever, right? And for everybody, it's not that each lab needs to do it for themselves, right? Because the annotations seem to be...
You do, because, because as I noted, you're going to do some annotations for a certain type of scans, a certain type of pathology, and then the other lab is going to want to use it, but their scans are going to be different and the network is not going to work. When I say narrow AI, it's very narrow AI.
So it's very specific
they're
to
very
the specific...
Yeah, because pathologies and organs are very specific. This is the nature of the problem. Okay. So here's an example of how this, an example for interactive learning for user corrections. You train a network with very few data sets, 8 scans. Okay, I should mention that each one of these manual delineation takes over 1 hour from an expert radiologist. And then when a new scan comes in, you're going to generate an initial segmentation. This segmentation is going to have an error, of course. You're going to ask the radiologist to make manual corrections, and you're going to get a network that learns specifically on this scan what were the corrections, okay? Because now you can take the user-validated segmentation, you can take the segmentation of that specific slice that was generated by your network, and then you're going to overfit the network to do the corrections that you have here. Okay, here's an example of what this would look like. This is a slice, and you see here in the initial segmentation, what you see here in brown is the fetal body. And you see that there are errors, okay? All this part is not smooth. And here you have a part that is not part of the fetus, okay? And this is the manual corrections. A radiologist has corrected this manually. And now what the network does is that it takes this and does the training in a way which I will show now. And now it generates the next slice. And this has to happen, of course, almost in near time so that the correction happens. Now you see the next slice has better quality than the other one. For example, here there are less things to correct. And down here, this is almost gone. Okay. So if you do this process one after the other, you're going to generate both a validated data set and a corrected data set in a few minutes. Okay, so this is the architecture. This network has to run in near real time to allow the corrections. So you have a first phase in which you have a feed forward up to the loss layer. And then after the user corrections, you do a back propagation. Okay, then you're going to segment the next slice and compute the corrected slice. Okay, and this happens in about 1.2 seconds. This is what it looks like, and this is the average over 30 cases. Here you see the volume overlap difference. So at the beginning, at time 0, there's 100% error. As the radiologist does this manually, after more than an hour, the difference between two radiologists is about 10%. This is the observer variability. And you see that the two radiologists did more or less the same amount of work. If you use a network that was trained only with 8 examples, you will get an error, you will start much lower. So the error is about 35%. However, notice that the time to correct them is almost as the time from starting from scratch. So this means that a network trained with not sufficient examples is going to require as much work as it did. In contrast, if you use the methodology that I just showed you, the initialization and the correction learnings, now the time is shortened in a very significant way. It's only 8 minutes to reach the same observer variability. Okay, so this is what you would do for the first few tens of data sets so that you can generate high quality segmentations. Okay. So now you have, you apply this process, you have now obtained 10 to 30 high quality annotations. You didn't have to spend 1 hour each, but now only 5 to 8 minutes on each one of them. And then, but the problem is that this network is still going to be fragile. It depends on the scanning protocol and many other things. So the challenge is how do you extend the coverage? And basically to do that, you have to process hundreds of scans automatically, okay? But they require validation. Somebody has to look at the scans and say, this is an error, this is not an error, and so on. And this is very time consuming, okay?
Can I ask you, Leo, can I ask a question? You mentioned something about dependency on the scanning protocol.
Yes.
Does it mean also it depends also on the machine that does the scanning or the hospital that does?
Absolutely.
So your narrowness is really narrow because if it's
very
a specific device and specific protocol.
Absolutely. Mm-hmm.
I see.
Okay. And the trouble is that it doesn't generalize well. It's very brief. Even the resolution doesn't generalize well. This is the challenge. So you've chained. So I go to Hadassah, I get the data sets, I train on them. I got data sets now from Ichilov. It's most likely not going to work very well. Okay, this is the problem. So what we want to do now is now to scale this up to acquire more high quality segmentations, but this requires validation. Okay, and this is the way we do this in the second stage. We have an approach which usually finds a region of interest with one network. So this is one network that knows how to find a region of interest, in this case, the brain, and then a second one that generates a prediction. Okay, I'm not going to go over the details. This is a custom architecture we developed to deal with different types of resolutions. But let me show you what happens with the uncertainty estimation. So let's say that this is the segmentation of one of the slides that you got. You see here the brain, the fetal brain is here, and here you see it's a clear segmentation error. Okay. Now, if you are able to quantify also the variability, meaning you also want the uncertainty, here shown in blue, there are areas in which this uncertainty is going to be a clear error, but other areas in which it's legitimate variability. Of course, you cannot know ahead of time what is variability and what is error. For that, you need a radiologist. However, if you can compute the uncertainty, you're already in good shape. And this is the way you can do that. You can use a common technique called prediction time augmentation. You basically take your image, generate a number of augmentations, and generate a number of segmentations. On purpose, you do intensity, shape, and location variations. And basically, you align them back and get, for example, an average prediction. In this case, we managed to eliminate the errors. So basically, you take the areas in which the network has a higher amount of certainty. In this case, but this is only in this case, you're able to eliminate the segmentation error. And this is what this technique has been used for other purposes. However, what we can do is that because we're processing a series of slides, you can build a network which basically takes this corrected segmentation and feeds it with two channels, the scan slices around it, and this segmentation, and produces the next one, just like in the iterative way. So this is an example. This is the segmentation. We see here that a whole part of the body was missing, and this is how the network managed to do this correctly. Okay. How do we do that? Well, we do the following. If you don't just take the average like I did before, but I combine all these, okay, into to compute the uncertainty. What you see here now in blue is going to be the network uncertainty. This is the voxels in which the network is not very sure of itself. Okay, the red one is the consensus. Okay, and there is a low, and you see that some areas there is a low uncertainty, and these are probably the legitimate observer variabilities that we saw before. Okay, now, which ones is worth looking at? If you have several of those, you can measure the area or the volume of the uncertainty and basically rank the slice uncertainty. And this is simply the sum of voxel predictions. You take the binary entropy of the different predictions, and this way you can give an estimate of what is the uncertainty. Slices and scans with high uncertainty, you say these are worth having a radiologist look over and tell me what is the right result. Okay. So you can prioritize the scan or slice inspection by decreasing order of uncertainty, because this means that you're acknowledging that your network is not very sure about it, so you can go and combine that. So the idea is very simple. Here is results. Okay, so we did experimental results for the fetal body, the fetal brain, and the placenta. You see here the unusual load. You started for the fetal body, for example. We started with 13 scans done manually. We trained with 9 scans and tested with 5 scans. This is the usual split. But once we get high quality results that are corrected, then we take these and and test it with many more scans. Okay, and we do the same thing for the brain and the placenta. And what you can see is the following: if you measure the dice coefficient, which is the overlap between two volumes, and the surface distance, you can see that the network achieves a dice coefficient and a distance which is very close to the observer variability, which basically means you've achieved your result. Okay. The placenta, for example, is much harder, and so you need more examples to start with, and this is very typical. Certain applications require more manual, fully manual delineations than others. Okay. Now, how do you do the prioritization? So the idea is the following. Let's say that we take the scans and you basically randomly take the 55 scans and you want to validate them and you want to correct the errors. Okay, and so this is the orange line is the sequential or the random order. If I correct them in the order of decreasing uncertainty, not only scan-wise but slice-wise, you can see that I can reach the observer variability of 0.09 with only 12% of the slices. So by inspecting 12% of the slices, I get this entire body to reach the observer variability. Okay, and this is instead of 33% if I were doing this without prioritizing. Okay, so the inspection and correction of 12% of the slices basically achieves the observer variability with no prioritization. So basically it saves a lot of time and produces the right results. One other aspect of this has to do with active learning. So here you see the training size from 5 to 30 and the mean dice coefficient. You can see that the network is very sensitive to what do you choose to train the network on. So obviously you can do worse with 20 scans than with 5 scans, depending on how you choose. But of course, the idea is which scans do you add? Because it's very expensive to add the segmentations and the corrections. It's best to choose to do better in the choosing of them. So with the methodology that I showed you, just adding 5 scans already achieves a much better result, especially for the surface distance. Okay, so this basically has to do, how do I choose 5 scans to optimally improve the performance of the network? Okay, and here we see that the correlation between the estimated uncertainty and the actual one is quite good. Okay, so just to finish this part, now we have a network that has been trained for all 3 structures and have created 290 very high quality segmentations that have been approved by a radiologist with a relatively modest effort, because we didn't have to look at all the scans, and already extended this to the different protocols. You see here the different names here are the protocols and the scans, how the networks are trained, and in all cases that you see that the numbers are very high. Okay, so basically we were able to process and validate a high number of scans without incurring in a very high cost, and this also has a certain range for the developmental curves. Okay, we use this data to create for the first time this development curve. So this is an earlier work that we did. We published this development curves from MRI, and now we're in the process of extending these development curves to 500 fetuses with the network that we have just trained. Okay. Any questions up to now?
Yes. Are there any certain rare pathologies that simply don't have enough data to be able to build something like this? Like you just don't have enough scans?
Yeah, if you don't have enough scans and it's very rare, then you might not. Every pathology and structure requires a different number of scans, and you don't know ahead of time how many of those you're going to require. With this methodology, you can discover on the go what's missing. Okay.
So have you seen anything like that? Have you kind of had experience with something that you haven't been able to use because it's something?
I'm not pretend to solve all the problems in radiology. So I pick the problems where there's enough data, but definitely there are cases in which it would not be possible to do it. Okay. I'm gonna skip this part in the interest of time, but I'll just mention that we are able also to do this with linear measurements. In other words, how do you get one single measurement without doing any kind of segmentation? So this requires picking the right slice and then doing a single measurement here. This is a ground truth which is easy to acquire. It requires a radiologist to look which slice is relevant and make a single measurement. This can be done in a few minutes as opposed to more than an hour for the full segmentation. It's intuitive and familiar. It's not as good as a volumetric one, but it's certainly useful from a clinical point of view, and it's similar to what would happen in ultrasound. So here we use the same methodology, but now we build a network that basically performs one network to do the slice selection. Here you see in yellow a network that manages to choose the correct slice. And then once the slice is chosen, we can use model-based methods to basically derive the measurement. Okay, so we were able to develop this type of network with only about 200 linear measurements. Okay, I'll skip the numbers, but basically we achieved an observer results as good as observer variability in a very short amount of time with very few data. Okay, so that I can finish on time and allow for some questions. Basically, I've described to you with one single example a method that can achieve clinically useful results, can quantify the observer variability, and do this with a very small training set. I showed you a network that is able to do active learning from the corrections and prioritizes the radiologist's time by estimating the segmentation uncertainty. And this tool is currently in use for research at the Tel Aviv Sourasky Medical Center, who developed this with us. So basically, the message I want you to get is that to do this properly, you really need the radiologist in the loop, and you really need a bootstrapping methodology to create these annotated data sets. And as I said before, we applied this to a number of other domains in which the number of scans that required is relatively low, 100 for liver ones, and also about 100 for OCT scans for ophthalmology. So the take-home message is that the segmentation of medical structures is really unique and different because the annotations are very time-consuming. You want to have a radiologist in the loop to be able to do earlier deployment, and you should be able to estimate the observer variability. This is a long list of the collaborators. The ones in blue are for the fetal ones and the other projects. This is what the teams looks like, and thank you for your attention.
Thank you, Leo. Any questions from the audience?
Yes, I have a naive question.
Sure.
You said that labeling the data is a laborious task, but let's say 100 hours or so, or even 1,000 hours for actually solving a problem of medical examination doesn't sound like a very high price for what you get. Okay,
that's correct, but let's think what happens in practice. A radiologist hour is about $200 an hour, number one. Number two, you have to get the scans, which you all have to pay for. And number three, radiologists hate to do this because their job is to treat people, not to segment data sets, okay? So the companies, if you translate that into money and effort, it's several $1 million for a very, very single application. So companies such as Philips, Zebra, or others do spend this money to do a few of them, okay? But what about all the others? This methodology is really about speeding this up and reducing significantly the cost.
Thanks.
Mm-hmm.
More questions?
Can't we collect the data during normal treatment? As in they do their, radiologists do their work. Can't we collect the data when they do their normal work? Why do we have to collect the data?
Because you don't have the delineation. You collect the data. The data is collected in the sorry. The data is collected in the hospital a data set, but who annotates it? You need the annotations. Nobody does the annotations. It's not part of the clinical routine.
It's not computerized. How do they do their work?
They simply don't do it. They write a report in words. They don't do the annotations. It's not part of their work. Otherwise, they wouldn't be able to treat so many patients.
I have another question. Is usually in machine learning, we need very big sets of data, right. Tens of thousands. How do you do here? How do you get along here with 100 records? How do you do that?
Well, I just showed you the methodology. You train a network that does mistakes and get a radiologist to correct the mistakes in a very efficient and optimal way. So you're going to need the radiologist, but it's going to be done in an optimized fashion.
Leo, you mentioned that the radiologists in normal life take basically they issue written report. They don't actually mark anything. They just have a written report. So why don't train the neural network to produce this written report? Why go through an intermediate stage?
The written report is semi-quantitative and has some issues with that. Producing the report requires medical knowledge, which is well beyond what is in the image. So this is it requires general AI. This is the short question. It would be excellent if we could do it, but I have no idea of how to go about this. I mean, we know how to do very narrow tasks for the time being.
Thank you.
Thank you.
Leo? Is there a paradigm to do some unsupervised feature extraction on
yes.
this test?
This has been tried. It works for some amount of cases, but in the end, it's been shown, I mean, very clearly that it's better to go with a few annotated cases and add to that. So there is research on that, but especially for the segmentation part, it doesn't produce very good results. It doesn't mean it's not going to work in the future, but it's still under investigation. You will need, the bottom line is you still need some annotations and you still need a way to identify the rare cases.
Okay, thanks.
Thank you.
Leo?
Yes.
I have another question regarding the training process.
Mm-hmm.
I understood the general idea, but I'm not convinced in theory, why does it work? I mean, I understand the fact that once a radiologist tags the outputs manually, then you get a very accurate supervisor. But I don't understand how you prevent overfitting, even though you get it. Because if you train only on 20 images, I don't see how it...
Okay, so the answer there is technical. First of all, it's you have slices, so it's 20. If you have 8 data sets, you have about 800 slices, number one. Number two, you adjust the loss function, the augmentations. I mean, you have to work it so that the network, this network I showed, which I didn't go into detail, exactly has a set of parameters that prevents overfitting. Otherwise, you end up exactly like you mentioned. So what you see here is a customized network that prevents this overfitting from happening. Yes.
Okay, thank you.
Okay, so I think we're out of time. I don't want to keep everyone here. Maybe you can contact Leo.
Thank you for the questions.
Yeah. Thank you everyone for listening. Thank you, Leo, for the great talk. And we'll see you all next week.
Thank you.
תודה רבה.
תודה רבה.
תודה.
Thank you very much.